Broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome to our webinar on testing the Valleylab FT10. This is Jack Barrett and thank you for joining us this morning or afternoon or evening, wherever your location may be. Greatly appreciate you spending time with us this afternoon, again, or morning or evening. So our topics for discussion this afternoon, we will not, in the interest of time, be going through the theory, some of the background on electrosurgical units, nor will we be diving into the 60601-2-2 standard. We'll touch on that a little bit when we get to high frequency leakage, but we won't again spend much time in diving into that standard. During the course of the PowerPoint presentation, I will be using some video clips and talking through the video to show actual testing for all the primary procedures here, doing the REM, power output testing, high frequency leakage testing. At the end, we will open it up to questions, and we'll spend whatever time we can with answering those questions. I will be recording, or I am recording, this presentation, so I will share with you all the link for it so you can come back and look at it for future reference as need be. Our focus point, as we said, will be the Valleylab FT10. This, as you probably all know by now, is the replacement generator from Medtronic / Covidien / Valleylab of the force triad. And as you look at the front of the unit, some pretty clear differences between this generator and the force triad. One screen, pretty obvious, broken into 4 quadrants. The upper left is dedicated to Monopolar 1. The upper right of the screen is dedicated to Monopolar 2. And Monopolar 2 energy port is where the Valleylab mode is available as well. Bottom left-hand side is the Bipolar output. Bottom right-hand side is the LigaSure output. Another difference here is that the UFP port is integrated into the Monopolar 1 energy output port. Some pretty big changes in size and weight of this generator compared to the triad. Roughly 30% reduction in size and weight. And from a procedural perspective, it's 100 times faster than the force triad. So we're sensing density in tissue as the surgeon is doing a procedure. We're sensing changes in the tissue much, much faster. Again, 100 times faster, which to the patient is going to be pretty important. As we switch over and look at the rear of the unit, you'll see that there are just 4 foot switch connectors, the 4-pin associated with Monopolar 1, and this pretty much aligns with the segments on the front display. Monopolar 2 is the 6-pin, and of course the 2 additional pins have to do with the Valleylab mode. The Bipolar, the same 3-pin as you've used previously. LigaSure, there is only 1 foot switch connector now, the purple one. The orange one is not there. And then you have ports for the smoke evacuation, communication ports. So as they continue to implement changes into the FT10, such as networking, the automated OR, if you will, although I think they call that something different, all your ports are located there on the back. One of the other differences that I didn't mention on the preceding slide was the red scanning lights are no longer there. They now utilize a RFID chip in the LigaSure port, so they sense the presence of that instrument differently than they did in past times. So jumping right into the PM, we'll be starting with the REM. And historically, you've done this a couple of different ways. You may have used a different analyzer to do your REM testing. Quite often, you would have used a resistive decade box. But we are going to do our demonstrations with a product that Rigel Medical manufactures. Surprisingly, I know that we're going to use that product, the Uni-Therm, for demonstrations. But we'll be showing you how to do all the testing with that generator. But the test process is going to be universal for a number of different analyzers, quite frankly. And the other thing that I like to share with you is that the test process is going to be very similar from generator to generator to generator. So the connections that we're making to the analyzer, whether it's a Valleylab or whether it's an Irby or a Condit or whatever you might have, the test process itself is fairly similar unit to unit. What's going to change is resistance load values and such, but the actual process is going to be fairly consistent. Big change in how we test REM. With the Triad, with the FX, with earlier units, we used to start at 120 ohms, connect the generator to our test circuit, whether it was a decade box or whatever, and we would increase the resistance up until we got an alarm. We record that alarm, then we would back down, record the lower limit, which typically would happen around 4 ohms or so with a forced Triad. And we would also look for a 40% increase. So if we set a resistance, a load resistance of say 60 ohms, reconnected that REM circuit to the generator, we would expect an alarm around 82 ohms or so, because the Triad and earlier units would alarm two ways. One, if a maximum or minimum resistance was reached, or if we saw a 40% increase in resistance. With the FT10, we do this very much differently. One thing always to remember is set your resistance value and then do your connection, because the generator is going out and pulling that resistance value at about 70, 75 hertz or so. So it's always going out and looking for that value and making decisions based on that value. The REM test on the FT10 we do not do in clinical mode, but we go into the service mode, and we're going to use 4 set values. We're going to test at 100 ohms, we're going to test at 50 ohms, we're going to test at a 0 ohm or short circuit, and we're going to do a test with that port open or affinity. And for each one of those, we're going to have to set our resistance value. We're going to have to manually turn on the RF generator and look at what the unit says it sees as a resistance value. When I say the unit, that would be the FT10 generator. So let's start with our first video, and I will add some commentary as the video progresses. So we're going to use a REM cable with the white plastic pin on the cable itself. You see me pressing the tools button, and we're going into service mode. We're going to enter in the same password as we had on the Triad, which is 423213. RF output test. We're going to select pure for monopolar cut. Doesn't matter what our wattage is set for. I'm going up now and I'm going to make the second connection to our REM test circuit. But before I do that, I'm going to set the resistance value for 100 ohms. Make the final connection. And down where it says REM ZMAG on the screen, you'll see that we measure in 103.6 ohms, which is within the acceptable range of what we're looking for. Now I'm going to decrease the resistance down to 50 ohms. This screen that we're seeing on the FT10, when you're in service mode on the Triad, this was actually into center screen, but we never really paid a whole lot of attention to it. There are two measurement points internal to the FT10. You see that we measured 54 ohms in this case. I'm going to short the two connections together now for our 0 ohm. And you see we captured 1.7 ohms of resistance there. So in actuality, that REM cable that I'm using has some resistance associated to it as well, as you can see. Now for the last step, we are opening the circuit. We measure 1344 ohms. Our limit here is anything below 2000 ohms is acceptable, and our REM test is now complete. So as I was starting to say before I went back to the test screen, that center screen used to be live in the Force Triad in the center display, but we never really paid a whole lot of attention to it. In this case, we are going to be using that screen, as you saw, for the REM test. There are two internal current transformer, primary and secondary, so we'll be able to see and compare what the generator thinks it's producing for current, power, and such versus what we're actually measuring. One thing to note is that secondary measurement point is the closest to the output of the FT10. So let's minimize that screen for now. And we're back to that overall test screen. So just recapping, set 100 ohms, our range is 93 to 107. Set for 50 ohms, our range is 43 to 57. Short them together, should be somewhere between 0 to 4 ohms, and we were 1.7 or so. And then again, an open circuit, we want to see something less than 2000 ohms. So we will advance now into our power testing. If you ever attended one of the Covidien classes, they would show you how to do the testing on setups such as this, where we would utilize external power resistors and external current transformers. So that big gold rectangle at the bottom of the screen is your power resistor. That thing to the left of it is a current transformer. So we went from an active output, a wire through the center of the current transformer, through our resistor, back to our patient return, and then the output port of that current transformer went up to what amounted to a digital voltmeter, high accuracy digital voltmeter, but a digital voltmeter nonetheless, and we would be looking at current that way. A universal test process, no doubt. Disadvantages here is, as you see from those connections, there's plenty of opportunity for you to become part of the circuit yourself, which you try to avoid. And also, all of this testing and all your testing really should be done on a non-conductive surface. A lot of folks would have these resistors mounted to a wooden board. Never want to be doing this on an ESD mat, because that could add error to your measurements. You are picking up some stray capacitance because of that mat, and that would influence the readings. And one thing we should comment again as we start to talk about power testing is we always think of this as a pure DC resistance. We're setting 300 ohms, or we're setting 500 ohms, or we're setting 100 ohms, what be it. But really what's important to the generator is the impedance of that value, because we're switching, I think this unit, if I remember correctly, is switching somewhere around 450 kilohertz. Any inductance, any capacitance that is part of your measurement circuit, either internal in the analyzer itself or with external leads, can have a tremendous impact on your measurements, and to the point where if you're not careful, you can think a unit is out of calibration because of increased inductance and capacitance. You can make yourself go through the process of doing a calibration, and the concern always is then, are you actually adjusting it out of calibration or not? Think back to that screen that we were looking at. One of the things you can take a peek at when you're doing a power test is what the impedance that the FT10 is sharing with you that it's seeing, and that impedance again is the DC resistance influenced by inductance and capacitance. So we'll be doing our first test on Monopolar 1. The good news here is the number of power tests that one must do has been greatly reduced. We were fortunate enough to have a working relationship during development of this process. It's one of the topics that was a discussion point. As you remember with the triad, the FX, you do every power test on every energy port. So with Monopolar, you do it on Monopolar 1, you would do it on Monopolar 2, you would do it on the UFB port as well. Now with the test process for this generator, we're going to do but one test on Monopolar 1, and that is going to be a coag test. And then we're going to switch over to Monopolar 2 and do all our other associated tests on that energy output port. So on the picture of the FT10 itself, you'll see that the upper left-hand side quadrant is energized, telling us that Monopolar 1 is our chosen port. Below that is a connection diagram that is on the side of our analyzer, and this shows up on the display when you're about ready to do a test if you choose to show the diagram. And it just shows basically what we had in that earlier photo with the external power resistor, the external current transformer and such. We're coming from the active output port of the monopolar output. We're showing cut, but we're cut and coag comes out of the same port on this unit. And we're going to the top end of a variable resistor bank, which is set for 300 ohms, which is what they specify for a test for cut. For the actual coag, we'll be using 500 ohms of course. Through the MD measuring device, which is in fact our internal current transformer. So we are actively measuring RMS current, and then back to the patient return. On the right-hand side of this slide, you see what the test screen would look like on the Uni-Therm as it records the data. So we show the load resistance, we provide the true RMS power, true RMS current, RMS voltage, peak voltage. We also measure and provide now peak-to-peak voltage, which is not on this photo. And we also give the crest factor, which is simply the relationship between RMS voltage and peak voltage. In a cut waveform, the amplitude of that waveform is constant across the entire profile, across the entire process. So that ratio is pretty consistent. When we go to coag, it's more of a sinusoidal amplitude riding on the waveform. So you're going to see when we do coag tests that the crest factor is going to increase. The blend waveform is the combination of the two. A lot of folks will call that as well. They have proprietary names for it. The Valleylab mode is really a blend waveform dedicated to a certain surgical procedure. Other folks may call this effect, and all it is changing what the waveform looks like between cut and coag and the duty cycle of same. That gives you various elements onto the body as we're conducting, or as the surgeon is conducting the procedure. So as I mentioned earlier, the basic process here is going to be identical, regardless what generator model or manufacturer we're looking at. For instance, the connections will be the same between a Valleylab generator and an Irby generator, except Valleylab for cut likes 300 ohms. Irby will have you do that test at 500 ohm load resistance. When you look at the service manual for the FT10, it'll talk about using RF mode, which is that mode that we did our REM test in. As you see, there's a bit more button pushing with that. And with the Uni-Therm, we have gained approval for use of foot switch adapters or foot switches during the course of the testing. It just cuts down on some of your interaction with the unit to conduct the test, with the end game in mind of saving you time. Now, you saw me during the REM test push the little tool button on the bottom right center, if you will. And when you press that button, this comes up and gives you some options. So we have the demo mode, and that's where we used to do a lot of our testing with the Triad. The only thing that we really had to go into service mode for was the LigaSure testing. So we did all our monopolar, all our bipolar tests in demo mode, and we'll do the same here with this unit. When you go to Valleylab mode, that would be done in the service mode, as again, LigaSure is still done in service mode. So looking at the service manual, it will have you do a power test on Monopolar 1. We're going to do coag spray at the maximum output setting of 120 watts. And we're going to be looking for a current between 424 to 570 milliamps being the target. A lot of your generators will do pass-fail based on power output. That power output is typically plus or minus 15, or more typical, plus or minus 20%. For the Valleylab products, they have settled in and will use current as the pass-fail mechanism. And then you see the second half of that slide talks about how you would do your testing on Monopolar 2 for coag. So we do a couple of different settings. We do 2 at spray at the minimum wattage, at the maximum wattage, and at full grade. So let's see what actually happens here. I'm going into demo mode, enable demo mode. I'm using a REM connector that has that white pin removed, so it's a little different than what we use for our REM testing. Notice that my display is not active yet until I put my pencil in. You don't have to worry about holding the button down on this unit. That was a bit of a concern on the Triad, where you're supposed to press that and release it a little bit, but you can just hold that button, set it for your power. In this case, we're looking for 120 watts. Selecting power test, continuous power test, which is where with the Uni-Therm you spend the majority of your time. Setting my load resistance. Load resistance on this unit goes from 5 ohms up to 5,115 ohms in 5 ohm increments, as you saw. And it's rated for a full 500 watts continuous operation for a full minute, which is pretty heavy duty. I'm selecting coag. I'm selecting 5 seconds for my on time, 5 seconds for my off time. Once I get there, show diagram. We took a look at this earlier. So for my active electrode, through my resistor, through my current transformer, here's the connections on the side of the unit. and then back to the patient return. Now I have cables going from the front of the Uni-Therm there, and they go to foot switch adapters. So we're mimicking the foot pedals. I hit the start button twice. You see that segment energized. Coag comes on blue for 5 seconds, and there is the data that we capture. Now, a quick comment on this. When we're doing a manual test, as we just did, that information will not be saved in memory. We have test sequences all set for a bunch of different generators, a lot of different manufacturers, models. And when you do one of those test sequences, the first thing the generator or the analyzer will ask you for is to enter the asset number. So all of that test data that you just saw is associated to a certain asset number. And there you then have your data traceability. So that was a test on Monopolar 1 for Coag. Monopolar 1 is now done. That's pretty sweet. Now we're going to switch over to Monopolar 2, and we're going to do a couple of tests here. Notice there's a little micro switch in that energy output port. So a test pencil helps greatly because you don't want to be pushing that button while you're trying to measure energy. You're too close to the action. Set the unit for 10 watts. I'm going to change my display. Now I'm doing this again manually. In the test sequences that I mentioned, all of these screens would be preset. So all the values would be preset as well. So you wouldn't have to worry about remembering. Covidien likes 300 ohms for cut, 500 ohms for Coag. Everything would be preset for you. And again, of importance here would be what that current value is, 181 milliamps. That will be the driving factor as to whether the service manual says that is good or not. And as we see, our acceptable range was 143 to 223, so everything is proceeding nicely for us. Now I'm going to do the same thing, but I'm going to go into service mode. So I'm selecting Monopolar 2, pure, setting for 10 watts. Now I'm going to start my Uni-Therm measuring. I'm going to hit activate. I'm going to watch the front panel in the Uni-Therm, so while the LEDs are lit, I'm going to keep it activated. When that LED goes out, I'm going to hit deactivate. And as we go back up, we measure the same current, which is probably a good thing at this point, huh? So those are the two different ways to test. Again, the service manual would say do this all in service mode. It's a little bit more time consuming, as you can see. And again, we have received approval that a number of these tests, including what we've just done and shown you, can be done using our foot switch adapters. So Valleylab mode, I'm not going to show how to do this test, but again, this would be only available on the Monopolar 2 energy port. If your surgeons don't ever use Valleylab mode, you probably have a decent argument to save yourself a test. Not the greatest photo, but as you look at the right-hand upper energy port, you can see that that is a Valleylab, what they call the Triverse pencil. And that is a 3-button test pencil. So you have coag, and then you have the Valleylab mode as well. And when you go into Valleylab mode, the display gets a little different on you. But again, we're going to test at a power setting, 75 watts. We're going to look for output current anywhere from 433 to 581 milliamps to determine whether that is acceptable or not. So next test we're going to dive into is bipolar, and you can see in the photo of the front of the FT10, again not the clearest, the brightest photo, but you see how I've moved my test leads down to the bipolar. Below that is the little screen that shows the connections to the side of our analyzer or to whatever you're using for your load. So we're coming from the active output, which would be the left-hand port. We're going from there through our load resistance, which for Valleylab, they talk about 100 ohms for your bipolar output testing, through a little jumper, through the current transformer, and then back to the dissipative tine or dissipative port on the generator itself. And again, on the right-hand side just shows the data that is being captured during a test. Note that it always does show you what that load resistance was set for. So we have 3 tests that we're going to do, or that the service manual has you to do. The process is the same, so I'm just going to show you one. And again, all the rest of them would be done exactly the same, no wiring changes. All you're doing is dialing in a different power setting. Notice here we have 2 little micro switches, and sometimes a right angle lead as I'm plugging in there will not capture both of those closed. So just reach in, latch them, and you see that bottom quadrant of the display become active. So I'm going to go to the highest power setting. I'm going to select bipolar. I'm going to reset my load resistance. With Valleylab, bipolar is always cut mode operation. Diagram, just as we saw before, active output through our load resistance back through the dissipative tine. And we're capturing 959 milliamps. I'm going to run the test again just to show that when the generator is active, that quadrant of the display lights up. Now you might ask why it lights up blue rather than yellow, and I don't have an answer for you. And just to tie that loop up, the range was 843 to 1133, comfortably right smack dab in the middle, just about. So we're going to jump to LigaSure now. Couple of difference here as well as to what we can do for settings with LigaSure. You'll see this as we start to go in and show the video. But we used to set 3 current values. We'd start at 1 amp, we'd go up to 2.7 amps, and then we would go up to 5.5 amps. And of course, this would be all done in the triad. We actually call this debug mode rather than service mode, where we would set our current value. You'll note here now with the FT10, we're going to set a couple of different effect settings as you're going through a full PM, and we're going to set a couple of different power settings. As we talked about earlier, there's no scanner now in the FT10, but there is an RFID chip in the LigaSure tool itself. One other comment before we actually go to the test video. And while we talk about 350 watts or what used to be 5.5 amps, notice our acceptable range is 1940 to 2.7 amps. In an actual procedure, we are running in what would be called a closed loop mode. So we're actually sensing the density of the tissue as we're doing the procedure. As those forceps starts to close onto the vessel, we're looking at what that impedance is how that impedance is changing as we're grasping and sealing the vessel. We can't do that actually with a set impedance as we would have with a test resistor or with any analyzer. So we're not actually going to see that full 350 watts because we're testing a little bit differently. We're still testing, of course, closed loop, but we don't have that varying tissue resistance, varying tissue density. So with this particular unit that I'm doing my testing on, we're going to see that we're measuring about 2.2 amps. One other thing with the LigaSure port designed as it is, you can't get right angle test leads in there. So I've borrowed some other test leads that I was using for my foot switch connectors before. I'm entering in the password to go into service mode. I'm going to come down and I'm going to select LigaSure for my energy port. I'm dialing in maximum power. If you had the old connector that extended those cables with the 2 little fixed dots on them, that would not be recognized any longer by the unit because there's no scanner looking at dots. For LigaSure testing, I select a value for my load of 50 ohms. I'm going to hit the start button twice. I'm going to activate the generator. My LED goes out. I'm going to hit deactivate. See some of the background of the video room that we've installed in our Tampa office. And so here's our outputs. We measure 253 watts, 2.2 amps of current. So if you watch the table on the left-hand side of the screen there, you'll see IRMS, VRMS, P average. Again, that's being picked up in 2 different points within the FT10 itself. But if you look especially at SFZ mag, that is the resistance or the impedance now that the generator thinks it sees as it looks out at the load resistance of your analyzer. And again, the DC resistance, the capacitance, and inductance all come into play. and something to watch for, because if you're using a test load that is significantly different, that's going to have a significant impact on your measurement criteria. So you don't want to be making what in process would be a good decision based on bad data. So that's our LigaSure test. And just a couple of screens that I captured. So we've done REM, we've done power output testing on 4 different energy ports: Monopolar 1, Monopolar 2, Bipolar, and LigaSure. LigaSure, of course, is bipolar in nature. Now we're going to jump into high frequency leakage and cross coupling testing. So if you ever have the opportunity to visit one of the generator manufacturers, they all have this infamous wooden table with their generator and all the leads very well defined as to the layout of where they need to be. The height of that table is well defined, and all of this comes into play with this 60601-2-2 test standard, because for a manufacturer, they cannot exceed 150 milliamps of leakage current on single fault condition on any of the energy ports. Now, as a manufacturer, they can define something less than 150 milliamps. There are some manufacturers that for a certain output port will specify 69 milliamps as pass-fail. This is always done with a fixed 200 ohm resistor. On the Uni-Therm, we have those located on the side of the unit. They're independent resistors, not attached to our load resistor, or load resistance bank, I should say. And again, the limit is 150 milliamps. Now, as biomeds, we don't have to have this table. We don't have to have such an exacting layout. But what we should try to do is ensure that our leads are as short as possible, that the leads are not coiled, that we're not adding capacitance by them looped across a chassis, or opportunity for cross coupling between one lead to another, or coiling it to get some additional inductance in the test lead. It's interesting, when I do these presentations live at a trade show or a biomed show, during the high frequency leakage portion of the discussion, I always do an active demonstration where I take that long pencil cord, coil it up, press it on top of either the generator or on top of the analyzer, and rather than seeing 73 milliamps of leakage current, I can get up to 450 milliamps of leakage current by adding inductance and capacitance. So very, very important. Something to keep in mind if you have a test that's failing. Take a look at your leads, make sure everything's laid out, pretty short as possible, and a good opportunity to save that generator, pass the test, without going to the famous wooden table. So when we're doing high frequency leakage testing, we test the active and the dissipative electrodes separately. We always test in a single fault condition. So in this case, we're going to test an active with the return open. We're going to test the return with the active open, so that would be the single fault condition. And our limits are 150 milliamps or 4.5 watts through the 200 ohm resistor. So now with the Uni-Therm, and that's the one of the test screens on the right center and lower center of the display. And I guess one thing that I should comment on here is when you look at these test screens, when we're doing power testing with the Uni-Therm, we allow you as the biomed to select whether you want to look at a test screen or not. When you're doing high frequency leakage testing, every test screen is slightly different than the one preceding it. So we kind of do force you looking at a display to make your connections. When we talk about our auto test sequences, we have the right connection diagrams implemented in the test procedure for what you're trying to do. There's connections on the side of the unit. So in this case, we'd be coming from into that left white jack there. That would be either the active or the dissipative electrode coming in. Our other electrode would be open. And we're going through our current transformer through a jumper link, through a fixed 200 ohm resistor to ground. And there is our test circuit for doing high frequency leakage. Again, always single fault conditions, always at maximum power output for that energy port. So let's run a test. There's our test circuit. And there is the leakage current that we captured, 41 milliamps. Now my next circuit is, my single fault condition is an open, is going to be an open active. And 123 milliamps is what we measured. I have noticed that typically your open active electrode, where we're looking at leakage currents through the dissipative, is always going to be a little bit higher than what you're seeing on the open active. And I have also noticed that coag, especially spray coag, seems to be higher in leakage current than some of the other tests. So that was monopolar. Testing LigaSure is going to be much the same, except we're kind of doing a bipolar test. Notice that they have specified 130 milliamps is the maximum amount of leakage current that they want to see on the LigaSure port. So while the 60601-2-2 specification still talks about 150, as a manufacturer, they have chosen to specify something less, 130 milliamps in this case. They never could specify, again, anything more than a 150, or they'd be in violation of the standard for ESU generators. There's also, we did this on the Triad as well, except we didn't quite call it this, but cross-coupling testing. Inside the generator, there's a little steering circuit. So when you select a energy port, be it Monopolar 1 or Monopolar 2 or Bipolar, LigaSure, whatever, when you energize that energy port, they want to ensure that there is very little, if any, current also being entered or flowing through the other energy ports. So if we energize Monopolar 1, we're going to look at the energy coming out of Monopolar 2. We're going to look at the energy coming out of Bipolar, and we're going to look at the energy coming out of LigaSure to be ensure that there is no cross-coupling, if you will, hence the name, that we get energy, unexpected energy, out of one port when we energize our needed port or our selected port. So you can see here I'm connected to bipolar. I'm also connected to Monopolar 2. Zooming in on the test screen. We're using a 200 ohm resistor for this test as part of the specification. And we're seeing that we got less than 1 watt of power. We were energizing the bipolar, and we were looking at the power coming out of Monopolar 2, if you remember that test diagram. So a little different than what this drawing shows us, but again, we were looking at energy coming out of monopolar tube when we energize the bipolar output. And you want to be sure that that energy output is minimal. Not unusual to see the less than 1 watt, less sign on current, and that's just really indicates that the steering circuitry is doing what it's supposed to do, and we're not getting any unexpected energy out of a port, because there still could be a patient at the other end of that port. So running nicely on time here. That kind of is the end of the testing. One thing that I mentioned is that when we're running an auto test sequence in our ESU analyzer, this thing called the Uni-Therm, we capture test data, all associated to the asset number. So this is just a little snapshot of the type of information we capture. So it shows you the test date, the time, the asset ID, what the test sequence was that we utilized for this test, some user comments that assist with the setup and what we're trying to do in the test. Then if you go about 2/3 of the way down, just lower than halfway, you'll see the actual outputs of a test, where we capture what the resistance value was, everything we saw on the screen, the resistance value, the output wattage, true RMS power, true RMS current, RMS voltage, peak to peak voltage in this particular case, what the crest factor was, and it was indeed a bipolar test. So all of that information is captured, and that gives you all the data traceability that you could ever possibly need. God forbid there was ever an incident and they came back and said, when was it tested? What did you test? How did you test? How it tested. You have all of that information readily available. So I do try to keep this kind of non-sales pitch. Obviously, I use the analyzer that we manufacture for the demonstrations. No surprise there, I guess. I would like to just put in a quick plug for this organization called META. META is a national association of biomeds, people like yourselves. This is not a replacement for your local biomed associations, kind of a supplement to it, if you will. Or if a local association is not convenient to you, it still gives you an opportunity to be part of some biomed organization. We are national in scope. I say we. I sit on the board of this organization. We are in a bit of a transition as we develop our intentions and the results that we're looking to achieve. Best news, if you go to mymeta.org, you can join for free. And we're looking for volunteers to assist in a number of different areas. The other thing is we do have this handbook available to you free of charge, either a hard copy if you like, or we can email you a PDF, which is a guide and covers some of the history of electrosurgical generators. We start with William Bovey and the first procedure that was ever done with an electrical surgical unit, accomplished in Boston back in, I don't know, 1920 something, 1930 something, I don't quite remember. Any questions at all? If you like a copy of that, my email is shown there. My cell phone number is shown there, and I will now open this up for questions. So if you use the chat function, you can send me a question, and we will take it from there. So it helps if I go to the right screen here on my computer. Okay, so the first question, clearly this is a current customer of ours. Thank you very much. I do appreciate it. And the question is the automated test available for the FT10? How can we gain it? We make all of our test sequences available to our customers without charge. So drop me an email there at jackb@seaward-groupusa.com. Apologize for the length. It's not the shortest email that was ever designed, but it does get to me. And I will send you along a small file that includes all the sequences that we have. My disclaimer on this always is there's a bunch of sequences in there. Some I have written, some other folks from Rigel have written, some our distributors have written, and some that our customers have written and shared with us. I can't tell you that I have tested all of them myself, but I've never had anybody come back with disastrous results from any of them, so they're all safe. So drop me a line, and they're yours to be had. A comment, good demo on the ESU. Thank you, Gil. Thank you, Hugo. Eric, sorry, I need to go all the way up. Let's see. May I get a recording of this video? Absolutely. As part of the registration process, I now have access to all of your email information, and I will share with you certainly. It may not be until later today or tomorrow when I get it out to you, but yeah, I will share with you a copy of our recording. How can I get a paper copy of the slideshow? I will give you a recording. I can certainly do a PDF version of the presentation as well. And if you'd like to have that, again, I won't send that to everyone. But if someone does want a PDF version of the slides, I'd be very happy to share that with you. And again, just send me an email and I'll get that to you as soon as I can. And some nice thank yous, which I greatly appreciate. So again, if you are a current customer, thank you so much for your business. We do really truly appreciate it. If you're considering moving forward with us, I hope you found this helpful as well. I'm a little prejudiced, but it is a heck of a unit. With that said, I am like right on time, 3 o'clock on the button. Let me just check to see if there was any more questions that came in. Looks like we are good. So again, thank you all. I will end the recording. I will end the presentation at this point. And again, really do appreciate your time. You don't get enough credit for all you do. And there are those of us out there who do appreciate what y'all do because you keep it all going, keep it all together. Thank you.